Welcome back. Let's consider an example problem. Basically, we've got CO2 gas where the temperature and pressure are given to us, and we're going to basically look at this gas at a very high pressure. We'll talk about what that word high means and how we quantify high in a minute. But ostensibly, the reason we're looking at this is we're pumping this gas into a well in order to reduce the viscosity of the oil in that well. This is an example problem from Fundamentals of Thermodynamics by Sontag. In any case, we want to find V, and given two independent intensive thermodynamic properties, the others are determined. This state postulate or state principle, which is really a specialization of Gibbs phase rule, is what we're using here to basically say, well, if I got the two, the other one is given to me. The governing equation that would give me that third property is the equation of state, which is determined by the substance and the phase. In this case, the phase is gas. And so we have a number of options for modeling that gas: ideal, van der Waals, Redlich-Kwong, or we could just look up the data for that gas in a table if it's available. So we're going to consider all four of these in this little video. The ideal gas law, we're all pretty familiar with that, hopefully. Specific volume here is equal to our gas constant, which is substance specific, times the temperature over the pressure. Here the temperature is in Kelvin, the pressure is in kPa. The volume here is going to be in meters cubed per kilogram. It's a specific in volume, the intensive volume. R here is going to be in kilojoules per kilogram per Kelvin, as we'll see in a second, and as we will hopefully remember throughout this entire class. Van der Waals equation is basically written in this form to kind of show us, this is kind of like P times V equals RT. It's written to kind of show us the relationship to the ideal gas law. PV equals RT, but in this case we've got correction factors of A on V squared in the first term and minus B in the second term. These correction factors basically make up for the fact that the ideal gas law considers all of these particles to basically be point masses that don't interact with one another. They just fill up the space. Here we're going to allow for those intermolecular reactions and actions to matter. A is given to us in terms of the critical point properties of T critical and P critical. I've written it like this: 27 on 64, which is a pure number, multiplied by RT on P critical squared. RT on P, that should be units of volume, so this is going to be a volume squared times P critical. So the units of A here should be volume squared times pressure. We can also get that by just looking at this expression here, and since this term we have P being added to A on V squared must have the same units as P for the dimensional homogeneity of this expression to really work out. And what that means is that A has to have the units of ultimately P times V squared, as we just saw, or kilopascals times meters cubed per kilogram quantity squared. B, for the same reason, we have to have dimensional homogeneity in this term, so V and B must both have the same units. B is another constant that's given to us in terms of the critical point properties, T critical and P critical here. So the difficulty with using the Van der Waals equation is that we can't solve this explicitly for V, and of course we're looking for V in this problem, so the ideal gas law is nice. We can explicitly solve for it, but it may not be appropriate, and so that's why we're going through this process here of trying to figure out how to use which one of these equations and when their applicability makes them most useful. We could rewrite this expression, though, in terms of an implicit form, a function PV of t, or PV in t, equals 0. And we want to find the root of that, basically, knowing P and T. So if we were to bring the RT over to the other side of the expression, we have this is now our function f, and we want to know the value of V that would make this function of f equal to 0. Before we take a look at how we do that root finding, let's take a look at the critical point properties in R. The critical point properties can be found in our book, Introduction to Thermal Analysis by Moran and others, as in table T1. Unfortunately, they don't give us R directly, which I think is just an oversight, honestly. But nonetheless, they do give us the molar mass, and they give us directly the critical point temperature and pressure here. We typically want to work with pressures in terms of kilopascal, and they've given it to us here in terms of bars. So we need to go ahead and multiply this number by 100 to get it into in terms of kilopascals. Um, Notice also that each one of these critical point properties is substance specific. In fact, it kind of acts, the critical point properties act as kind of a fingerprint for that substance. In this case, substance doesn't necessarily mean a single chemical molecule, for instance. It could be just like air, which is a blob of stuff that we have a kind of standard value for. Um, to get R, which is the gas constant for each one of these substances, what we're interested in is basically taking the ideal gas constant, which is universal in terms of kilomoles, and rewriting it in terms of kilograms. And the way that we do that is ultimately we divide by the molar mass. So I've reworked the basic conversion from our standard form of the ideal gas law that we all learned in chemistry to what we really are more interested in this class, which is P times V, which is the specific volume, equals R, which is the substance-specific gas constant, times T. And the reason we do this is we work with kilograms an awful lot as engineers, and we want to be able to do that easily. And so we just go ahead and rewrite a gas constant for each substance by dividing R by the molar mass. And that's pretty straightforward. What is important to realize is that when I go ahead and take this value and I divide by the molar mass, I'm basically going to be multiplying by kilomoles per kilogram. I'm going to get kilojoules per kilogram per Kelvin. This is a unit that we really need to become familiar with in this course. It's the unit not just of the gas constants, but of also the specific heat capacities, and we'll also see of the specific entropy. So really take note of this unit and begin to work with it, I think is what I'm trying to get at. The value of R that we would find in this particular case, taking our universal gas constant and dividing it by the molar mass of CO2, is about 0.1889 kilojoules per kilogram per Kelvin. So that's how we get our values that go into the ideal gas law and the van der Waals equation. And in a minute, we'll see those also go into the Redlich-Kwong equation of state. But let's also consider the answer just really quickly. Going ahead here and doing this in MatLab pretty fast, we can see that the solution is pretty straightforward. Most of this is really just inputting data. But when we input the data, we should go ahead and use comments to put the units in for any numerical values. That'll really help to keep track of units in the code as well as on your actual in your actual work on paper, but especially when you're actually going ahead and computing numbers, to keep track of the units is important. Line 4 computes the gas constant, and then we go ahead and compute our quantities for A and B using our formulas. We keep track of the units here, as we should. And then line 15 is kind of the first really an interesting line. It's defining a function in MATLAB, a one-line function, so to speak, called an anonymous function. The way that we read this is f, and then the equal sign is read as is, so the assignment, copy assignment is an is. If f is, the at sign here can be read as is a function of. So f is a function of, and then whatever the variable is that we're going to allow for in the rest of the line. So there can really only be, in this equation here, one unknown. The rest of the actual parameters that are placed here have to be defined. So for instance, R has to have a value beforehand. T has to have a value beforehand. The only thing in this expression that is allowed to vary, that is considered to be a true variable or an argument, is V. So this is our expression for our function for the van der Waals equation. The magic happens in line 16 where we find the root. We basically pass it the function and then also the initial guess. So in this case, we take the ideal gas explicit relationship, giving us an actual number as the guess for the van der Waals equation of state. And then we also put semicolons at the end of all these lines to comment or to suppress the output. And then line 17 actually prints out to the screen the values that we're really looking for. And that's kind of a common way of working with MATLAB that prevents our screen from being cluttered. Also note that line 1 is critically important. This is the initialization of the MATLAB workspace. We should never neglect it. But if we take a look at the output real quick, we can see that the ideal gas volume is more than twice the van der Waals volume. So something is really different, and probably the ideal gas law is not a very good model to use in this case. But let's go ahead and take a look once again at how line 16 maybe actually is done in the computer. Root finding is the process of finding where a function crosses basically the x-axis, or where it f goes to 0. And so we're ultimately looking for this value of v. This is what we'd call the root of our function here. And the way that we do that is we have a guess, and we use that guess and the value of f, and then probably the value of the derivative at that location, sometimes computed numerically in the computer, in order to create a linearized approximation of that function f near this initial guess. And this linearized approximation would be y minus the 1y that you know, f0 in this case, equals our slope. So that's going to be the value of f prime at this location, times x minus the 1x that you know. In this case, x is our v value, and v naught is, so the naught here stands for our initial guess, v naught and f naught. So we could take this and then use the fact that we really are looking for when will I get this value of f to be 0? So setting y, which is our value of f, our linearized value of f, to be 0, and solving for this next value of v, setting that equal to v1, where y1 would be 0, we are going to get an expression that v1 would be equal to v naught minus f naught on f prime v naught. So this is going to be a closer approximation. It'll be right there in this particular drawing of our actual root. And then we could actually generalize this and repeat the process using this as the next guess. And we can do that until we get an acceptable error. So until our value of f that we actually find is very close to 0. And this technique is called the Newton-Raphson root finding technique. MATLAB has a bunch of these built in or canned root finders. F0 is one of them, and it does a number of things, not just Newton-Raphson. I'm not even sure if it actually uses Newton-Raphson, but it does a number of techniques in order to try and converge quickly to that root for you. So we ought to use those whenever we can, and we have in this case. So root finding is a good thing that we really want to be able to do. It's a common thing to have to find the root of an algebraic expression in engineering, and so using MATLAB to do that is really kind of giving you, in some regards, the keys of the kingdom to doing many engineering problems. But we really want to talk also about the Redlich-Kwong equation of state. It's a little bit more exciting. It looks very much like the van der Waals equation of state and the ideal gas law, except now we've got our expression that is adding to p here has got a little bit more complicated denominator. It's not just v squared anymore. It's v squared plus b times v. And also our constant a here is no longer a constant. It depends on our temperature. So we've got these pure values, pure numbers, once again for a and b, but now they're multiplying, at least in the case of a, an actual variable. So t is showing up here inside a. This t is inside a, so a is a function of t now. So this is a little bit more complicated expression, and it's definitely something we would want to use MATLAB to do, because even doing this by hand would be a little bit tedious. So we want to solve this implicitly using MATLAB. But we also want to consider maybe scaling this problem, and it will prove to be quite useful. So to scale something is really no different than when we scaled the volume by the mass. Here we're going to scale by dividing by constants. And in this case, let's divide the pressure by the critical pressure and the temperature by the critical temperature. And we're going to call the values that come out of those p star and t star. The star stands for a dimensionless value. It's really a percentage. It's the, so to speak, the percentage of p critical that p is, or the percentage of t critical that t is. And then we're going to allow v star here to be equal to v over some characteristic value of v that we're going to kind of let the algebra determine for us. We're going to do that by really requiring that each term be order 1, and that means not too big or too small, as we'll see in a second. So if we were to plug in all of our guys here, so for V we plug in VC times V star. For P we plug in PC times P star, and so forth into this expression and kind of massage things around. We're going to find something, but let's do it term by term. I think it might be a little bit more helpful in a kind of a practice way. So V minus B now, this term, is just going to be VC times V star minus B, and there's our B value. And we could pull VC out from all of these guys, and we would get this kind of an expression. So VC times V star minus this guy times our T critical and P critical divided by VC here now, because we've pulled a VC out that wasn't there. And we're going to actually call this value here now B star, which is just our original B value divided by VC. And so now we've got V minus B can be written as VC times V star minus B star. Let's do the same thing for the next term. We're going to take P and time or plus A on the quantity V squared plus B times V. Let's replace all of our variables here by what they will be in terms of their starred counterparts. So P is just P critical times P star. A is all of this stuff, where T over T critical already shows up for us as T star. R T critical squared on P critical, there it is. And then we multiply this by V squared, which now becomes VC squared times V star squared, plus B, which is going to be our B value is just VC times B star, times V, which is VC times V star. And all that to the minus 1 power. Again, we can factor out a VC squared in the basement here. And we get another expression now, where now we can write this guy, which was our A, divided by previously V squared plus BV, now is going to be divided by V star squared plus B star times V star. This guy now is going to we're going to call that A star, and it's just A over P critical VC squared. Notice we're dividing A by really what it's a quantity that has similar units. So A had units of pressure times volume squared, so we're dividing by the pressure scaling and the volume scaling squared to get an A star. So let's continue now by plugging these guys both into the Redlich-Kwong equation and finishing things out. So P has turned into this, the P term. V has turned into this, and we've got R times T, where T is just going to be replaced by T critical times T star. If we go ahead and pull out the P critical VC from the left-hand side, divide through by it, we end up with something on the left-hand side that's remaining that is dimensionless. And we can see that because everything that remains is starred, and all the starred guys are dimensionless quantities. And the starred variables, which include P and V, are order 1 dimensionless quantities. They're percentages of either the critical pressure, or in our case an undetermined VC, which we're going to determine right now. The way we're going to determine that is that we can see that these percentages, this is all percentages over here, are starred dimensionless quantities, is being multiplied by an invisible 1. The weighting on this side is basically a 1. And if we want T star to also be a percentage that is nicely sized so that both sides of this expression really can interact with one another, then the weighting on this side should also be 1. And RT critical on P critical VC, that is a weighting. These are just constants that are being put together, and this is in fact dimensionless. And we're gonna set this to be 1 so that both sides are order 1 or weighted equivalently in terms of being just percentages of the scaling values. So that means that VC should actually be equal to RT critical and P critical. That's what VC should be if we want these two sides to be sized so that they can interact with one another appropriately mathematically. So this is not the critical volume, so to speak, the volume at the critical point. It's called we'll see that it's called the pseudo-reduced volume scaling in a second, but it is the proper scaling here for this kind of equation of state. And with it, things really simplify. A star, which we had on the page before, was just RT critical on P critical VC, that quantity squared multiplied by 0.42748 T star to the minus 1/2. Well, now this guy has become a 1, so A star has really become simple. Similarly, B star had RT critical on P critical VC. That's become a 1 because we have our choice for VC, so B star has become very simple. Our expression in the end for the Redlich-Kwong equation, now that it's scaled, is very nice, where we've got our critical values scaling for pressure and temperature, and we've got correspondingly RT critical on P critical. This is a mistake, being the scaling for V. So let's fix that real quick, as we can see from right here. So in any case, we've got this very simple dimensionless reduced form we'll call in a few minutes, and it's very nice to work with a form like this where everything has been sized appropriately, especially when working with numerical methods like on the computer, because the computer has a tough time with numbers that are too small or too big, especially when we're adding numbers, one that's very big and one that's very small, for instance. That loss of significance that can really undermine our ability to use the computer to solve. So we could use this same scaling, exact same scaling, with, say, the ideal gas law. And what happens when we substitute in for P, V, and T, and our critical values, VC being chosen to be equal to RT critical and P critical, we get P star V star equals T star. Very nice. This is a dimensionless expression that's exactly the same as before, only we've scaled it. We'll see what the value of that is in a second, besides what I've just said in terms of the numerical method. The van der Waals equation can also be scaled just the same way, using our exact same scaling as before. And once we work our way through that process, canceling out things, we end up with a very simple form of, this would be P star plus A on V star squared times the quantity V minus B equals T star, and where A star now is 27 on 64, a simple universal pure number. B star is also a universal pure number. And what really should be striking is that the R, the T critical, and the P critical are nowhere to be seen. Where are they? They've been sucked into the scalings. But what remains is true for all substances. There's no R here. It's true for all substances. We go back to our previous expression here. Where are all the substance-specific guys? They're in the scalings. But the actual expression for the Redlich-Kwong equation of state and the corresponding values of the parameters B star and T and A star here, they are universal. They no longer depend on the substance chosen. So we can go ahead and solve these pretty quickly now on the computer. Doing that is nice because basically once we non-dimensionalize by dividing by the scalings, things become dimensionless. To get things back into a dimensional expression, we multiply by the scaling. So the starred quantities are percentages of the scalings. So if we have a starred quantity, we multiply by the scaling to get back the dimensional quantity. So here is in lines 16 through 19, we've got the van der Waals equation. Lines 21 through 24, we've got the Redlich-Kwong equation of state. Pretty simple. And then we print out the values. We can see the ideal gas law, the van der Waals equation, and the Redlich-Kwong equation of state here. Again, we've commented the units. The only thing that's really different here is that we're working with dimensionless quantities, and we've actually used the ideal gas law expression here, scaled as the initial guess for our van der Waals equation, and then we've used that value from the van der Waals equation as the initial guess for our Redlich-Kwong equation of state. In any case, we now can see that the van der Waals equation and the Redlich-Kwong equation of state give pretty good correspondence to one another, but that the ideal gas law is quite different. We really want to be able to compare this to data. If we go and look at the NIST website and look at the chemistry webbook, which is free, and go ahead and type in for CO2 for our temperature, we can actually find at the 10 megapascal what our specific volume should be, and it should be about 0.00344489. This is basically the way to think about this is a basic data point. And so given the value of that from the table, we can now compute a percentage of an error. We'll go ahead and do that in line 28 here in 2728 and display it, and we can see that the Redlich-Kwong is the best by far, 0.03% error. Van der Waals is 0.1% error. Not, excuse me, 10% error, 3% error, 82% error for the ideal gas law. So ideal gas law is really a bad model in this case. And that kind of begs the question, how do I know when it is a bad model or not, other than just kind of, computing with one of these other equations of state? So let's take a look at that. In order to really do that, we need to talk about the value of these dimensionless forms and what we might be able to do with it. So the dimensionless forms, just as a recap, here they are. We don't really have to worry about the substance-specific quantities because they're in the scalings. They're basically in the scalings of the x and y axis. So these are what we call a universal form. They're dimensionless, and they don't depend on any particular substance. So they give us the simplest presentation. If we plot P star, if we plot V star as a function of P star for different values of T star, these are actually valid lines for any substance. So the curves are universal. It's nice. The starred quantities, again, are just percentages of the characteristic values. Now, no one actually plots V star. Instead, what they do is they go ahead and they plot basically V star on the V star for the ideal gas, which is going to reduce down to PV equal on RT. And so obviously that should be 1, and for the ideal gas model is 1. Here what we've done is I've done this computation, V star over VIG, using the Redlich-Kwong equation of state. And what I've got here is what's known as a compressibility chart, which is kind of badly named because compressibility really should mean something else. But nonetheless, what it's really telling me is the comparison between the value of the volume as it is and the volume that the ideal gas would predict. So if Z is 1, this compressibility, so to speak, is 1, we have a very nice agreement between the volume and that predicted by the ideal gas law. And what we can see by looking at this is that if the pressures are low enough, we're really close to 1 over here. But different temperatures, especially lower temperatures, so this is a T star of 1, and that would mean that we're at the critical temperature. We really deviate away from this value of 1 for the ideal gas correspondence, pretty huge for any values of pressure that are not small. And what I mean by small here now is in comparison to the critical value of pressure. So if I have small values of pressure, which means small in comparison to the critical value, I can use the ideal gas law. But if I don't, then I might be in trouble. If my temperature is low, then I can deviate greatly from the ideal gas model. But the higher the temperature, this number up here, this is for T critical, or excuse me, T star of 2. So this is twice the critical temperature, and I can see that I never really deviate too far from 1. And that means that for high temperatures, the ideal gas law is really good. So high temperature meaning high in comparison to the critical temperature. And so that's what we basically see here, that the ideal gas model is good for low pressures, low in comparison to critical pressure, or high temperatures. When people talk about this in terms of, basically engineering, they call P star the reduced pressure. Sometimes they denote it as PR, which is, I think, bad simply because it doesn't have units of pressure, of course. It's dimensionless. T star is called the reduced temperature. It's denoted with TR. Once again, it's dimensionless. So if you see these guys in a table, don't think of them as they are not merely pressures and temperatures. They are the reduced pressures and temperatures, and what that really means is the dimensionless ones scaled by the critical values. And V star is what's called the pseudo-reduced volume. And of course, it's not actually scaled by the value of the volume at the critical point. It's scaled by the value of Vc, which is our T critical and P critical. So what's really great is that if we were to say look at data on this, right? So if I go ahead and were to say look at the data, this is a chart out of our book Thermal Analysis, and what you can see here is a bunch of data plotted on the line for different substances, and the data really fits onto these curves. It, this reduction that we've seen with these universalized curves, they really apply to multiple substances as we said they would. And that means we've really hit upon kind of a fundamental physics here. We've reduced a lot of things down to some very simple curves, very simple expressions that are universally applicable. So this is very exciting, I think, example of power of dimensional analysis, especially in terms of experimentation. So this is actually the values that we ought to be using for the compressibility factor. What I had shown before is what comes out of just using the van der Waals equation, or excuse me, the Redlich-Kwong equation of state for approximating V. In any case, this is the compressibility chart, and so the value of Z being close to 1 means that we are good to go to use the ideal gas law. Z far away from 1, we should not use the ideal gas law. Just as a kind of quick last, for people who are interested, quick last way of how did I actually generate that compressibility chart that I showed you a second ago. Pretty simple. Something interesting to note. It actually uses nested loops, so it's a real use for that. If you've been learning about computational methods or programming, and it's very easy to generate in MatLab. There are a lot of nice tricks being displayed here if you want to work your way through the code in terms of how to make a legend and so forth. But in any case, this is basically our example problem, and tells us about compressibility, tells us about how to use the Redlich-Kwong equation of state as well as the van der Waals equation of state, and it really shows us how to do this in MATLAB effectively and efficiently. And that is this problem.